is into 11 की पावर, तो ये 3 into 7 की पावर 2 into 11, 8 माइनस ये 8 है।
Hello? Hello? Hello, are you able to hear me?
Yes, sir. Yes, sir. You are audible. Good evening, sir.
Good evening, good evening. So, are you able to see the screen?
Yes, I started with it. It's
Is it
visible,
okay?
sir. It's visible. Yes, sir. So okay, sir. It's fine.
Okay, very nice. So, yesterday we talked about quasi-linear partial differential equation, which is of the form x, right? This is deva u deva x.
Hello, sir. Writing is not clear, sir.
Pardon?
Right, this is This is not clear.
You are not able to read on the screen?
Yes, sir.
Let me use
Zoom.
All right. So what about this? Tell me, are you able to read now? X, Y, U, deva Y. Hello? Is equal to,
It's visible now, sir. It's visible.
is it visible?
Yeah.
Yes, sir. Yes.
Yes. Yeah.
All right. So this is the scalar equation, single equation. It is quasi-linear, right? Here, A, B, C, in fact, I assume that they are functions of class C1. So this is the partial differential equation, which is quasi-linear. Quasi-linear means it is linear in the highest order derivatives, right? But non-linear in U. Its coefficients, they depend on U. So that's why it is referred to as quasi-linear partial differential equation. Now, how to solve it? So I explained to this point yesterday that the best way, what is our objective? Our objective is to solve this differential equation such that along this curve, x, say y is some function of x, let me write phi x, this is equal to u naught of x. This is the initial condition. This is your Cauchy problem. Yesterday I mentioned about it. What is a Cauchy problem? Cauchy problem asks for determining the solution of a partial differential equation, right? Which satisfies the differential equation identically and takes on these specified values along that curve. So this, in fact, it is a curve because it is the intersection of two surfaces, right? It is the intersection of two surfaces. So this is your, let me call this initial curve. So I will denote it by gamma of xi. I can write the characteristic equations dx ds is your A, dy ds is your B, and du ds is your C. These are the characteristic equations, right? S is the variable. So characteristic equation, that is, this is your typical characteristic. from each point of gamma, a characteristic emanates. Okay? A characteristic emanates, and I explained it to you yesterday that the best way to solve the Cauchy problem is to look for characteristics emanating from each point of gamma in the direction of these characteristic curves, right? Thereby sweeping a surface. The union of all these characteristic curves, in fact, it generates the solution surface. These characteristics, they span the solution surface. So what is my objective? My objective is to solve these equations, to find these characteristic curves. So S is the parameter along this characteristic curve, and Xi is the parameter along this given curve. What is given curve? Let me write. The given curve is your X. I can parameterize it, and one should know that parameterization need not be unique, right? X is equal to Xi, and let me say that, oh, all right, let it be Y, in fact, okay? Let it be Y, let it be Y. Y is phi of X. Hello? Yes. Hello? Please speak.
Yes, sir. Yes, sir. Yes, sir.
So Y is nothing but phi of Xi, and U is nothing but U naught of Xi. So this is the characteristic curve, and I take this characteristic curve emanating from this point. This point, let me call this as Xi 0. That is, it is in the Xi-S plane, right? Xi is the parameter along this gamma, and S is the parameter along this characteristic curve. So this emanates from this point. Let me call this point as P. So P is a point which has the coordinates Xi, means this is the parameter which varies along this given curve gamma, and S is the parameter along this characteristic curve, right? S is equal to 0. S is measured from this point. So this is your S is equal to 0. So these are the conditions. So what is the problem? The problem is to solve this system of ordinary differential equations satisfying these initial conditions at S is equal to 0. Now you may recall the existence uniqueness theorem in the theory of differential equations. If the functions ABC are nice, right? If they are continuous and they are differentiable in the domain, then perfect, absolutely there is no problem. The weaker condition is this, should satisfy the Lipschitz condition. So if I assume that A, B, C, they are of class C1, means this system has a unique solution, okay? The ODE, so the problem of solving a partial differential equation satisfying an initial condition reduces to the problem of solving a system of ordinary differential equations satisfying this initial condition. Is that right? The theory of the existence uniqueness of ordinary differential equations ensures that if A, B, C, if these functions are of class C1, then this initial value problem has a unique solution. Is that right? So the solutions can be written as X as a function of X, and I can write Xi or S, or this is all right, as a function of Xi and S, Y as a function of Xi and S, and U as a function of Xi and S. Satisfying these conditions. At S is equal to 0, they satisfy. So this is, right, these equations, in fact, they constitute the solution of this initial value problem. Now, can you tell me what geometrically these equations, what do they mean? Hello?
Yes, sir. Yes, sir. Yes, yes. Audible clear. Yes, yes.
Geometrically, what does it mean? X, Y, U, it is a point in R3, right? X, Y, U is a point in R3, and each point is characterized by these two parameters, Xi and S. That is the locus of a point which depends on two parameters. What is that? Hello? What is that? It defines a surface. Is that right? X is equal to, if X is equal to X of Xi, Y is equal to Y of Xi, U is equal to U of Xi. The position vector of a point depends only on one parameter. What does it represent geometrically? It represents a curve in XYU space. Is that right? If it depends on two parameters, it represents a surface. Is that right? For example, if I say that x square plus y square plus z square, this is equal to 1, right? So you can see here that x can be expressed, x, all right, let x be x, y be y, then z I can write is square root of 1 minus x square minus y square. So look here, the position vector of each point is defined by these two parameters. What are these two parameters here? X and y. So the locus of such a point, in fact, turns out to be a surface in R3. But the thing is this, is it always possible to express S and xi as functions of x and y? Hello, somebody should tell me. Is it always possible to express S and xi as functions of x and y? We have got two equations involving two unknowns, right? X is a function of xi and s, y is also a function of xi and s. Now, is it possible to express s and xi always as functions of x and y? Hello? Somebody should be, this comes from analysis. Somebody should answer this question. Hello, is it always possible? Hello? Hello?
Yes, sir.
No, it is not always possible. You see, after all, what is this? It is a transformation. U is the unknown function. X and y are the independent variables. So it is a transformation from xy to xi s, right? If this transformation is 1, 1, means if the Jacobian of the transformation is different from 0, what is the Jacobian of the transformation? Xi s. This will be your what? X xi, y xi, xs, ys. This is the Jacobian of the transformation. Is that right? Hello? Hello?
Yes, sir.
Yes, sir.
If this is different from 0,
This is not equal to 0.
if this is different from 0, then we can always express S as a function of x and y, xi as a function of x and y, right? This is called inverse function theorem. So pick up any book on analysis. I think you should read, all young fellows, right? And you have a lot of energy and a lot of time. It is important to understand the basic essentials. If x is a function of xi and s, y is a function of xi and s, if this condition is satisfied, right, the Jacobian is different from 0, then certainly I can express s as a function of x and y, and xi as a function of x and y. And if I put here s as a function of x and y, xi as a function of x and y, this gave me the required surface. Hello? U as a function of x and y. Is it clear to you? Hello?
Yes, sir.
But this is possible only when this condition is met. So this is extremely important, right? If the Jacobian is different from 0, if it is non-vanishing so we are interested here at s is equal to 0. Because you see, locally, we are interested in finding out the solution locally in the neighborhood of gamma. Look here, this is something which is very, very important. In this analysis, we are looking only for the local solution. We do not know, even if the global solution, quite possible that solution may be global. But here, the local feature is extremely important. It is quite possible that you see it exists locally, but beyond this, the solution may break down. So in fact, we are interested only in the local solution, because if you solve these equations, the inverse function theorem, it tells us that in the neighborhood of the point, right, in some neighborhood, we can express s as a function of x and y, xi as a function of x and y. This ensures only in the neighborhood of that point. So here we are interested in finding out the solution in the neighborhood of gamma, right? And P is any point here. P is any point on gamma. We are interested in finding out the solution in the neighborhood of gamma. So that's why it's referred to as local solution. So what happens to, so we are interested in finding out xi at s is equal to 0. Xi at s is equal to 0. When we, yes, compute these coefficients at s is equal to 0, it is nothing but dx d xi, you see. This is nothing but dx d xi, this is nothing but dy by d xi, this is nothing but dx ds, this is nothing but dy by ds, ordinary derivatives, right? When we come to this point, because you see they are all continuous functions, so continuity ensures that if it is non-vanishing, it will also be non-vanishing. The continuity of these functions xi, yxi, xs, ys ensures that this Jacobian of the transformation does not vanish. If it does not vanish, then we can express s and xi as functions of x and y in the neighborhood of this point P. In the neighborhood of this point P. So this is a very important condition. This. Hello. Hello. Please take care of your mic.
Okay.
So if Jacobian is different from 0, then definitely s and xi can be expressed uniquely as functions of x and y, and when we plug these values here, we get the solution surface, and this solution surface is unique as a matter of fact, okay, uniquely specified. So this is a very, very important condition. If we are interested in finding out the solution of the Cauchy problem in the neighborhood of this gamma, which is the initial curve, first of all, we should check this condition. We should check this condition, right? We should check this condition that what happens to the Jacobian at any point here on gamma, if it is different from 0 for every xi, right? Xi, because this P is quite arbitrary here. I'm right looking for characteristics emanating from each. This is a typical point. So if it holds for every xi, means it has a unique solution. It has a unique solution provided, yes, there is one more condition. What is that? Somebody should tell me. Hello? This ensures that s and xi can be expressed uniquely in terms of x and y. Hello? Hello, somebody should tell me what is the other condition. If you look at this figure again clearly, yes. So look here, this is your gamma, this is your characteristic curve at this point. So if you evaluate this equation, let us evaluate, right? Let us evaluate this equation at this point P. If I evaluate this equation at P, what do we get? Hello? So evaluating this partial differential equation at this point P, because this is the relation which should hold at this point. This P is quite arbitrary, any point on gamma, this should hold there, number one. Number two, look at this condition, yes, this is equal to this, means what? A at P, P is this point having the coordinates xi 0. So in fact, it is a function of xi only, right? Ux plus B at P, this is your Uy, and this is your C, which is again P. So this, evaluate this at this point P. So this is the evaluation at P. Similarly, now look here, if the condition is given that Uxy is equal to, this is the initial condition, say Uxy is equal to U0, which is a function of X, what it gives you? This will give me Ux, if I evaluate it on the characteristic gamma, it will give me dy U dy X into dx d xi. Where is dx d xi? At this point P, plus dy by d xi Uy. This is equal to U0 dash xi. U dash means derivative with respect to xi. Is that right? Now look here, we have got two algebraic equations involving two unknowns, Ux and Uy. Is that right? So linear algebra. Now we have got two equations. If the determinant is different from 0, look here. If the determinant of the coefficient matrix is different from 0, no matter what is the right hand side, this system has a unique solution. Hello, is it clear?
Yes, sir.
Yes, sir.
So this condition, in fact, it ensures that no matter what happens to the right hand side, if the Jacobian of the transformation is different from zero, then the Cauchy problem has a unique solution, right? But what happens? What happens if suppose this vanishes? Suppose j xi 0 equal to 0. If this vanishes, hello?
Yes, sir.
Will it have a unique solution then? Tell me quickly.
Then either infinite solution or no solution.
Very good. Infinite solution under what condition?
Determinant not equal to 0.
Determinant equal to 0, that is fine. But
If adjacent matrix, augmented matrix,
very good, excellent, very good. The augmented matrix must be of rank
is equal to the rank of the
Coefficient matrix.
rank 1. Rank 1.
Rank 1.
Yes.
rank 1, right, rank 1.
Is AP, BP, CP, and the X prime, Y prime, U naught prime. This augmented matrix, the rank of this should be 1. Is that right? Then it has a non-trivial solution and number of solutions because we have only one equation, right? One equation and two unknowns. It will have infinite number of solutions. But all these solutions, they are differentiable. Very interesting. Is it clear? Hello?
Yes, sir. Yes.
A very important result is deduced, you see, from this analysis, that if the Jacobian of the transformation is different from 0, then we have a unique solution for all xi. This is very important. If this vanishes for every xi, then a unique solution of the Cauchy problem. But if this vanishes, if j xi 0 vanishes for every xi, let us consider it vanishes, it is quite possible. It may vanish only at one point, not at every xi. If it vanishes for every xi, then what is the requirement from here? It is very clear. The augmented matrix must be of rank 1, correct? Geometrically, what does it mean? If you look at it, AP, BP, right? ABC. What are ABC? Hello? What are ABC? ABC, in fact, these are the components of the characteristic. Is that right? Tangent to the characteristic at this point. Am I right? Hello? You see, this is the vector field ABC.
Yes.
I told you.
Yes, sir.
So ABC, these are the components of the tangent vector to the characteristic curve, whereas x dash, y dash, u naught dash, this is the tangent to the given curve. This is your characteristic curve, right? And this is your given curve. So this means that they are parallel. They are parallel. At this point, what does it mean? Means the scenario is somewhat like this. The characteristic emanates from this point, but at this point it is tangent. Hello, is it clear? Hello? This is your characteristic. It is emanating from this point, but at this point, you see, the tangent is common. Hello?
Yes. Yes, sir.
So this is a very, very important point that if this is the situation, then it will have infinite number of solutions, right? Ji, because it is very clear. You say we can have infinite number of, I will illustrate with the help of examples then. You see, examples are the best, means by which the difficult concepts are made easy. All right, let's take few examples. So, but by the way, I just wanted to say one thing more. This method may fail. This method may fail if the situation is somewhat like this. If the situation is somewhat like this, this is your given curve, xi, okay? This is your given curve. Now, what do we do to solve the Cauchy problem? We take characteristics emanating from different points of gamma, right? Suppose a characteristic emanating from here, it touches, it is tangent to this. Then what will happen? This is the point P, this is the point Q, this is the characteristic. S is the distance measured along the characteristic, right? I mean, parameter along the characteristic. Psi is the parameter along gamma. Now, this is the characteristic emanating from here, but at this point, it becomes tangent to this. Then what does it mean? Hello? Somebody should be able to tell me what will happen to this situation. Hello? Somebody should answer this. What happens in this case? It is quite possible. Am I right? This is your given curve. This is your given curve. And the characteristic emanating from this, in fact, touches this at some point. Hello? Somebody should be able to answer this question. No. Because we have already discussed it. What do you think? What will happen? This is the point.
Oscillating plane?
Pardon? Hello? What do you say?
Oscillating plane, sir? Indicate oscillating plane?
No. The question is this. We are talking about Cauchy problem.
Yes, okay.
We are talking about the Cauchy problem. Cauchy problem means the set of differential equations, ODEs, dx, ds is equal to a, dy, ds is equal to b, du, ds is equal to c, right? ABC, these components, they constitute the vector field. Is that right? Hello? And your integral surface is tangent to this vector field at every point. Correct? That's why we call it an integral surface. So what are the characteristic curves? I explained to you yesterday that these are the integral curves of the vector field. Is that right? Now here, this curve is such that, you see, if a characteristic emanating from here touches it here, then what will happen? Is it possible to solve the Cauchy problem in such a situation? Hello? The Cauchy problem may not have a solution, may fail. Why? Can you tell me? Hello?
Hey, Papa.
Yes. Please take care of your mic lest it may disturb others. Is it all right? Look here, these are the characteristic equations. So if a characteristic issuing from this point touches here, so what we do, you see, if this equation is integrated, many a times this equation is referred to as compatibility condition. And these are the characteristics as a matter of fact. But anyway, this kind of distinction is not very important. The thing is this, if I integrate this along this characteristic curve, if I integrate it along this characteristic curve, the value of u, right? Value of u, in fact, it will depend on this point. You are getting the value of u. You get some value of u here as you move along this characteristic curve. But the predicted value may not coincide with the value assigned at this point. Are you following? Hello? Along this curve, u is equal to u naught of x. I mean, this is assigned. U is assigned on this curve. Is it all right? The values of u are assigned along this curve gamma. Now, if the characteristic issuing from this point touches this at some point, what does it mean? It means if I integrate this equation along this characteristic curve, du ds is equal to c, the value of u predicted here by integrating it may not coincide with the given value. Is it clear to you? Hello?
Yes.
So the method may fail. So this method of characteristics might fail if this is the situation. All right, there are some examples. I think you will appreciate that if we just work out a few examples. That's very important. That's all right. So let's take this example. Deva u deva x plus 3x square deva u deva y, this is equal to 1, right? And so initial condition is u at x comma x cube, this is equal to 1. This is the initial condition specified. So how we start? we know how to solve Cauchy problem, right? This is your specified curve gamma, given curve. This is the given curve, okay? This is the space curve. Space curve, so I can parameterize it. I can write that x is equal to xi, y is equal to xi cube, and u is equal to 1. This is the parametric representation of this curve gamma. And I take it at s is equal to 0. S is equal to 0 means a point on, right? S is the parameter along this characteristic curve. Along this characteristic curve. So the solution of this, yes, characteristic curve, what is the characteristic curve? It satisfies the equation dx ds is equal to a. A is 1. dy by ds is equal to 3x square. And du ds is equal to 1. Is it all right? This is your characteristics. That is, characteristics are given by the solution of this system of ODEs satisfying this initial condition. Let me call this as number 1. Let me call this as number 2. So the characteristics are obtained by solving the system 1 satisfying the initial conditions 2, right? Is it all right? Hello?
Yes, sir.
If any point is not clear, please do ask. Don't hesitate. I think it's important. This is the purpose of this workshop. So if I integrate it, look here, x is equal to s plus some constant. Is that right? X is equal to s plus some constant. And this constant can be determined using the initial condition. So this implies that if I make use of this condition, s is equal to 0, x is equal to xi, and therefore constant is xi. So I get x is equal to s plus xi. Is it all right? Hello?
Yes, sir.
Similarly, the second equation. The second equation. What is second equation? dy by ds is equal to 3 xi square. So look here, 3x square, x I have already determined. So this will be your what? First of all, I'm supposed to write this x in terms of s, which I can do with the help of this previously obtained equation, x is equal to s plus xi. So let me write that 3 times x cube. So this is the integral because dy, I'm integrating it, right? 3 times the integral of s plus xi whole square ds. Is it all right? Hello, plus some constant? Please tell me yes or no.
Sir. Yes, sir.
Yes, sir.
Very good. So this tells me that this is equal to s plus xi whole cube plus some constant. Is that right? How I will determine that constant?
Yes, sir.
Using the initial condition. So when s is equal to 0, y is equal to xi cube. So xi cube, this is, let me write, constant. So initial condition, it gives me y is equal to xi cube, right? When s is equal to 0, the first term on the right is simply xi cube plus constant. And this gives me that the value of the constant should be 0. This gets cancelled. And therefore, y is s plus xi whole cube. Is it all right? Hello?
Yes, sir.
S is this expression, y is this expression, all right? So x and y, they have been obtained in terms of s and xi. Now once this is known, I can determine u from here. U is equal to s plus xi. Now u is equal to s plus some constant. And that constant is obtained using this. At s is equal to 0, u is equal to 1, so that constant is 1.
1.
Is it clear?
Yes, sir.
Yes, sir.
du ds is 1, and this condition is satisfied that at s is equal to 0, u is equal to 1. Is that right? Hello?
Yes, sir.
Very nice. So x, so look here, these are the equations which are extremely important. I will just mark x is equal to s plus xi, y is equal to s plus xi whole cube, and u is equal to s plus 1. Is that right? Now, what was the next point in this analysis? Jacobian of the transformation. That is extremely important. Hello?
Yes, sir.
We should find out the because that is a very important, very important entity. It will tell us whether this determination is unique or not, whether the solution is unique or not. So that is very important. So Jacobian of the transformation at xi 0. In fact, you see, this is a shortcut, but I should determine xi s. Okay, I should determine xi s and then take s tending to 0. But anyway, the result would be the same. Okay, because they are all nice functions. We have assumed that they are all nice functions. So j will be your what do you get? Hello, tell me. It is a transformation from xy, so it will be your xi, yxi, and xi at s is equal to 0. At this point, s is equal to 0 is nothing but x prime. So I should not. All right, this is your. So I will write xi s. I will write xi s. So this is your xs. This is your ys. Now if I evaluate at s is equal to 0. So this evaluated at s is equal to 0, it will give me x dash xi, ordinary derivative, y dash xi, right? This is your dx ds, this is your dy ds. Is that right? What is this expression? Can you tell me quickly? Hello?
Right, sir.
J xi 0, what is this expression? X dash xi. X dash xi, so x dash xi is 1, am I right?
Yes, sir.
Xi is 1, y dash xi,
So 1.
3 xi square.
3 days, yes.
3 xi square, so 3 xi square. Dx ds is given to be 1, dy by ds is given to be 3x square, and x is your, what is x by the way? X is your xi. On gamma, on this curve, x is your xi. So this is 3 xi square. Am I right? Hello?
Yes, sir. Yes.
What do we get? This is equal to 0. And it holds for every xi. Oh, very nice. I got the condition. So so if the question is like this, whether this Cauchy problem has a unique solution or not, you need not determine the solution. Only Jacobian will tell you the result. So in fact, even this much work is not needed. You can immediately write down J. You can see here, you look at the first column, look at the first row, 1 3 xi square, 1 3 xi square, because x is equal to xi on gamma. Is that right? Hello? X is equal to xi on gamma. And what is dx, ds, dy, ds? These are nothing but the coefficients. Dx, ds is 1. This is your 3 xi square. So it is very clear that from here, this is the Jacobian. And this Jacobian, in fact, turns out to be 0 for every xi. If the Jacobian turns out to be 0 for every xi, then what do you infer from here? If the Jacobian is different from 0, the solution exists uniquely. But if Jacobian vanishes for every xi, then we just discussed there are two solutions. Either there are infinite number of solutions or there is no solution. Hello?
Yes.
All right. How it will be decided? How did we decide whether there is no solution or there are infinite number of solutions? We look at the tangents. At these points, you see, isn't it? We look at this rank of points. That is A, B, C, and this is your x dash xi, y dash xi, and u dash xi. The rank of this matrix. Is that right? Hello?
Yes, sir.
So what is this matrix? First of all, it is very clear. It is your 1, 3 xi square, because you see, the first two columns, in fact, they constitute the Jacobian. The third one is right. We know that C is 1. C is 1. And what is U dash? U dash, you can see here that U dash is 0, right? U dash xi. On xi, in fact, U is specified as 1. Hello, is it all right? So U dash is 0. So this is your 1.
Yes, sir.
3 xi square 0. So you can see here that nowhere, you see, this is of rank 2, as a matter of fact. This matrix rank condition is not satisfied. So what do we infer from here? Hello?
No solution.
Very good, excellent. So all this work is not needed. I have to concentrate only on two things. Number one, because I'm interested in finding out the solution in the neighborhood of gamma. In the neighborhood of gamma. So in the neighborhood of gamma means xi, j at xi and s is equal to 0. Go to the xi s plane and j xi s. So now I know that this is the parameter along given curve, s is the parameter along this characteristic curve, and yes, this is your j. This turns out to be 0, and if it turns out to be 0, there is a need to find out the rank of the coefficient matrix. The rank of the coefficient matrix quickly, just by looking at these two, I can write this, and it is of rank 2. Rank is 2. Is that right? Hello?
Yes, sir.
Rank 2 means there exists a non-vanishing of order 2 by 2. So 1 by 1, 1, 0, you can see here.
Yeah.
Okay, very nice. So no solution. But you see, there is another method, I mean, which is very popular amongst the students, and also if you look at books written by Indian authors, they write Lagrange's equation. You remember Lagrange's equation? So what Lagrange's equations is a shortcut, but it's a very nice method and very helpful, but it doesn't tell us about the geometry. Yeah? So what is the, somebody should tell me at least this mechanical part. What is the Lagrange's method? dx upon?
1.
1, very good. This is equal to dy upon?
3x square.
3x square.
Wonderful. And what is du upon?
1.
Nice.
1.
What is the next step?
We solve these equations.
All right. So you see, these are the three ratios, right? These are the three quotients. This is equal to this is equal to this. Three ratios. So only two are independent. Is that right?
Yes, sir.
So I can take this is equal to this and this is equal to this, or this is equal to. Out of these three, I mean only two are independent.
Yes, yes.
So you get two solutions. And so what can you tell me quickly? What are the solutions?
So x equal to u plus c1.
U is equal to x plus c1 and first and third. Is that right?
Yes, sir.
And from here you can.
First and second.
Very good. Very
First
good.
and second.
Very good.
Plus C2.
First and second, y is equal to x cube plus c2. So I can write this as the first one I can write u minus x is equal to c1.
Yes,
And
sir.
what is the second one? Y minus x cube is equal to c2. Then what is the next step?
The general solution will be given by phi of,
Find a relation between C1 and C2.
yeah, phi of C1 C2 equal to 0.
So, or you can say that c2 is a function of c1, right?
C1, yes, sir. Yes, sir.
Now you see there is no geometry at all. Can you see it? U minus x, is that right?
Yes, sir.
This is the general solution.
Yeah.
Right.
Now how to get this general solution? We make use of this initial condition. We make use of this initial condition to determine this arbitrary function. Hello?
Yes, sir.
Yes, sir.
So what is the condition? Look here. When y is equal to x cube, when y is equal to x cube, right? What do you get? U is equal to 1. Or I think it is the best way would be u minus x, because u is the unknown. So the best way could be, yes, I can write this u minus x as a function of y minus x cube. Right? It is always better to write like this because I am interested in finding out u. Is that right? So,
Right.
yeah, so u minus x as some function of y minus x cube. I can write like this, okay? Let me write this as phi, and this is a different function. So u minus x is some function. Now using the initial condition, what do we get? U is equal to 1. U is equal to 1. Is that right? Initial condition, u is equal to 1. And y is equal to x cube, 0.
Which is absurd.
What do we infer from here? F
Which is absurd.
Pardon?
Yes. The right side is constant and left hand side is variable.
Very right. Never.
No solution.
This is not possible. Not
Not
possible.
possible.
Not, because it is very difficult to find, right? For different values of x, the same value. This is not possible. Is that right? Because x is a real number.
Yeah.
For you see, you go on varying x. I mean, you cannot find a same number. This f0 is a fixed number, and therefore this is never possible. So what do we conclude? What do we conclude from this Lagrange's method?
No solution.
No solution. Pardon?
No solution.
No solution. This problem has no solution. But you see, unfortunate part is this, there is no geometry. You cannot visualize what's happening. Mechanical way of doing things. You write these ratios, get these two equations, then you write like this, and then you argue like this and say there's no solution. So this is all right. This is what most of the books will. But if you look at good books, I forgot to mention books in the beginning. You see, Garabedian is a very good book. Garabedian, Paul Garabedian on partial differential equation. Please, you are all young fellows. You have a lot of energy, lot of time. So please read this book. I think it is very, very important to get geometrical insight into it. That what's happening in fact. Why the solution doesn't exist. Garabedian. The second book I would recommend, F. John. Have you seen this book in your library? A very good book on partial differential equations. It is published by Spinger. F. John, this is Spinger publication. Garabedian, yes, it is published by perhaps American Mathematical Society. I am not very sure, but English translation, right? Is a very good book. I mean, it's wonderful. F. John, Garabedian, and there is a book by Mac Owen. Very good book on partial differential equation. Mac Owen, and another book I would recommend. This is a complicated name. I think I have written somewhere. This is Sandro, S-A-N-D-R-O, Sandro Celsa. It's a very recent publication. 2008 or 2009, not very sure, but it's a very good book, right? The title is Partial Differential Equations in Action. Partial Differential Equations in Action, from modeling to theory. So this book talks about the models as well as theory. It's a good book. Then, of course, there is Oxford publication. This is Williams. It's also a very good book on partial differential equation. The full name is W.E. William. Again, partial differential equation and smaller. You see, I would be following these books as a matter of fact. Smaller. SMOLLER. The title is Reaction Diffusion Equations and Shock Waves. So 1994, I think 99, again, there is another edition. So this is a very good book. So 1, 2, 3, 4, 5, 6. I think these are very good books on partial differential equations. So I would recommend you people, those who are interested in applied mathematics, those who are interested in partial differential equations or ordinary differential equation, whatever, they should read this stuff. This is extremely important. Is it clear? Lagrange's method is, it gives us the result, but unfortunately you don't understand the geometry. But let me tell you now, because I have understood this feature, so I can explain this now. Look here. What is this? If you look at the solution, u is equal to x plus c1, what does it represent? Hello? U minus x is equal to c1. You get one solution, this you get another solution. Hello?
Yes, sir. Yes, sir.
What does it represent in the xy space, x by u space? Geometrically, u minus x is equal to constant. It is a plane, yes or no? You see, in 2 dimension, in the ux plane, it is a straight line, but in x by u space, you see, if I talk about this line, x plus y is equal to constant. What does it represent in xy plane?
Line, sir.
Line. But if I talk about this line in x, y, z space, 1 into x plus 1 into y plus 0 into z is equal to constant. What does it represent? It represents
Plane.
It represents
Plane.
yes, that's very important. This x square plus y square is equal to constant. What does it represent?
Circle in 2-dimensional and cylinder in 3-dimensional.
Very right, very good. So u minus x is equal to c1 is the surface in x by u, right? It's a surface. Y minus x cube constant is another surface. If two surfaces intersect, hello?
Yes, sir.
Surfaces intersect, look here. each member, because it's a family of surfaces. C1 is quite arbitrary, C2 is quite arbitrary. So I get two families of surfaces. Is that right? Hello?
Yes, sir.
And these are called characteristic surfaces because they are the solutions of the characteristic equations. You see, these are nothing but the characteristic equations. I could have written this as ds. So ds is equal to 1, ds is equal to 3x squared, du by ds is equal to 1. Is that right? It is not du dx as a matter of fact. It is dx ds is equal to 1. So don't think it is a division. Yeah, right? It is another way of writing a differential equation. Yes, what it is called? Differential form. Hello? Hello?
Yes, sir. Yes, sir.
So this is very important what I say. What I say that you say, you write this equation. I think yesterday I mentioned about it. M plus n y dash is equal to 0, right? M plus n y dash first order partial differential equation. That is m, which is a function of xy, plus n, which is a function of xy, dy by dx is equal to 0. What is the meaning of dy by dx, by the way? Hello? It is an operator. ddx is an operator operating on y. Hello?
Yes, sir.
It is not dy upon dx, but you might have noticed that we write very frequently this as m dx plus n dy. Yes or no?
Yes, sir.
I mean, that's a thing. We cannot write because dy by dx is not like, dy upon dx. No, it is not the ratio. It's not a fraction. ddx is an operator. ddx is an operator operating on y. We cannot write like this. But can you tell me what is this form, what it is called?
Exactly.
No. Exact. That comes later. My question is this, you see, if the differential equation is given in this form, very often we write in this form. But what does it mean? This is called differential equation. This is called differential equation. And what is called? This is called differential, right?
Operator.
No, you see, in fact, when you write dx and dy, what is the difference between dy and, yeah, right, and dx, dy? What does it mean, dx, dy? This is called the differential. Dx and dy, they are called the differential, right? I mean, this is the equation in terms of differentials. This is really the differential equation. But can you tell me what is the connection between dy and dx? No? Somebody should be able to tell me. This is calculus. It is taught at the 12th level. It's calculus. Dx, dy. Hello? You see, if you have a curve like this, and suppose this is your x, and this is your x plus dx. Dx, or you call it delta x, it is all right. I will call it delta x so that there is no confusion. Delta x, that is change in x. X plus delta x. So look here, this height is your y, and this height is your y plus delta y. Yes or no? Hello? So look here, this is the tangent at this point. Now this is the tangent line approximation, as a matter of fact. This is the tangent line approximation, you see. This difference is your y plus delta y minus y. So this is your delta y. This distance is a delta y. This distance is your delta x. Is that right? In the limit, when delta x goes to 0, okay, this becomes tangent. Right? It becomes tangent to this curve, the slope. So this is an approximation. So what is the approximation? I can write dy. It's another way of writing it. Dy, that is delta y, I can write dy into, yes, delta y is equal to dy by dx into delta x. What is dy by dx? It is the slope. It is the slope. You see, dx is this, it is the slope y. So this is the distance delta dy. This is your geometrical picture is this is your dy, and this is your dx. So this is very important. You see, you should understand that dy, now I can write dy as dy by dx into dx. So dx can be taken outside, so I can write this as m plus n y dash into dx equal to 0. Since dx is different from 0, this delta x I have written dx. You see, once you write delta x, it's very clear. When y is equal to x, you can see here that dx and they're same, right? dy by dx, I will write, this is dy by dx, dy by dx into delta x. You can see here that when y is equal to x, then dx and delta x both are same. So whether you write this as delta x or dx, it is same. Is it all right? Hello?
Yes, sir.
Does it make any sense? So I just wanted to explain what is the difference between the differential form and the differential equation. Both are same in this sense, because dy I can write, dy can be written as dy by dx. This is y dash operator, ddx operating on y. Don't think that they get cancelled. In fact, it was your delta x. And we have seen here the delta x, if I write like this, and if I replace y by x, this is ddx operating on x is 1. So dx is nothing but your delta x. So I can write this as delta x. Delta x is dx. Is that right? So from this, I get this relation that m plus n y dash into dx equal to 0. Since dx not equal to 0, I get m plus n y dash equal to 0. So this is derivable from here. So in that sense, both are equivalent. So you see, I just wanted to say this, when you write this form, Lagrange's form, this is the differential form, right? But whereas these are the differential equations. I have written dx, ds. This is a differential equation. But here if I write dx upon 1 is equal to dy upon this is equal to du upon this, these are the differentials, okay? But now the idea is very clear. I can write a differential form in terms of a differential equation. So anyway, so once I write like this, I get these two solutions. What does it represent? It represents a characteristic surface. Right? One family of characteristic surfaces. This is also another one parameter family of C1 and C2, they are the parameters. Is that right? Hello? C1 and C2, they are the parameters. This is another parameter. So, what did I explain? What are the surfaces? Surfaces, they are the union of characteristic curves. These are the curves which generate the solution surface. Yes or no? Hello?
Yes,
Hello?
sir.
So look here, a member of this intersects a member of this along a characteristic curve. Is that right? Because this is nothing but one parameter family of characteristic curves. Second one is also a one parameter family of characteristic curves. Each member of this family intersects a member of this family along a characteristic curve. And what is the locus of that? Locus. Locus is obtained by, yes, C2 as a function of C1. C2 as a function of C1 or this as a function of this, it gives us the locus. You see, the parameter gets eliminated. You know how to determine the locus? Hello? If I write that, hello?
Yes, sir.
The locus of, you see, I am interested in finding out the locus of intersections. And the locus of intersections is obtained by writing y minus x cube as some arbitrary function of u minus x. I have eliminated this parameter. So as a matter of fact, there is some geometry here, but not everything what I have discussed here. So you should understand both. You should understand both, right? That is very important. But at the same time, this analysis is also extremely important, whether the solution exists or not. The idea is same. The Jacobian of the transformation, you have to look at the Jacobian of the transformation. If it is non-zero, means one-to-one transformation. One-to-one transformation means, yes, inversion is possible. So implicit inverse function theorem ensures that S and Xi can be expressed uniquely from the solutions, right? S and Xi can be expressed uniquely in terms of X and Y. And therefore, we know that the solution exists and it is unique. And if this is equal to 0, then there, of course, there are two possibilities we have discussed. find out the rank of the rank of this. If the rank is different from 1 means infinite number of solutions. If rank is different from 1 means what? Rank is 2. If the rank is 2 means, hello?
No solution.
No solution. If rank is 1, infinite number of solutions. All right. So with this background, perhaps quickly we can work out one problem, and rest I will give you the exercise. So you please try these problems at home, and perhaps if there is any difficulty, we will talk about these difficulties later. So look here. Let me just write down what are the possibilities. The possibilities are j xi 0 if this is equal to 0 for every xi, right? This means what does it mean? If this is equal to this is, suppose this is, let us consider case 1. I will write like this. Case 1, if j is different from 0 for every xi, means what?
Unique solution.
Unique solution.
Unique solution.
Very good. Unique solution. Unique solution. Unique solution, but of no matter what happens to the right hand side, I have already explained to you. Number 2, if j xi is equal to 0 for every xi,
Either no solution or infinite number of solutions.
there are two possibilities, either no solution or there are infinite number of solutions, depending on the rank condition. Is that right?
Yes.
Depending on the rank condition. Number 3, that is very important. For every xi, it's quite possible that j xi equal to 0 for some xi. For some xi, say xi is equal to xi naught, some point. There is some point on gamma for which this is equal to 0, right?
Yes,
And at that point, this is your gamma for some xi, okay? This is your characteristic issue. This is the point xi naught, some specific. First and second, right? These are the conditions associated with every xi. The third one says, if this is equal to 0 for some xi is equal to say xi naught, then what can be said? Hello?
Yes, sir.
And suppose, you see, now, if this is a situation that it vanishes, j vanishes, please take care of your mind.
Yeah, yes, sir.
Then what happens? There are no C1 solutions under what condition? Yes, hello? If gamma is not a characteristic, at this point is your xi naught 0. Let me call this as P. I will call it P. If gamma is not characteristic at P, what does it mean? It means the tangent to the characteristic curve and tangent to the given curve. If these two tangents are not coincident, then there is no solution. No solution. But if gamma is characteristic, so this is one case. Second case, if gamma is characteristic means at this point, this is the second case. Gamma is not characteristic means this is the situation, right? Gamma is characteristic means, yes, it is like this. It is tangent to this at this point, x xi naught. This is the point xi naught. If this is the situation, if gamma is characteristic at that point, then a C1 solution may exist. If gamma is characteristic at xi naught, then a C1 solution may exist. If gamma is characteristic at that point, then a C1 solution may exist in the neighborhood of P. In the neighborhood of P only if rank condition holds. Rank condition holds. But if gamma is not characteristic at P, then there are no solutions. In fact, no solutions, what does it mean? No C1 solution, I should say, no solution in class C1. This is very important. No solution in class C1. Somewhat less regular solution might exist. Some less regular solutions might exist. So these are the cases, and you please, now time is up, but I will give you a few, just can you please note down these problems? Ux plus 3x square uy, this is equal to 1, and please work out, yes, with different initial conditions. That is, in this first is ux x cube is equal to 1, u at x cube is equal to 1, x minus 1, and this I have already done. The third case, u at x cube minus x is equal to x plus x square. This is question number 1. Please write down this question number 2 as well. Question number 2, please. This is, yes. Question number 2, ux plus uy plus u is equal to 1. And again, there are two cases. U is equal to sine x, y is equal to x plus x square, and x is greater than 0. So the second case, u is equal to 1 plus sine x. This is changed, right? And y is equal to x plus x square, and x, of course, greater than 0. Please work out, and this is the last one. This is very good question. That is, I will write that ux plus uy is equal to 1, u is equal to 2x, y is equal to x plus x square, and x is greater than 0.
It
Please.
is not visible, sir.
I'm sorry. I'm sorry. Yes. Is it all right?
Yes, sir. Yes, sir.
So you see, these are the three problems based on this material what we have discussed. So please work out these problems, and if there is any difficulty, please ask next time, right? And see this, these conditions which I have listed are extremely important. So all right, we will talk about these problems tomorrow, discuss and then proceed further. Okay.
Okay, sir.
Can I close the session now?
Yeah, sure, sir.
Yes, sir.
Thank you very much,
Thank
sir.
you very much.
Thank you, sir.
Thank you very much, sir.
All right. Thank you. Bye.
Professor Kapil Sharma is about to join.
Yes. What do you say, Dr. Chaudhary?
No problem, sir. I'm informing the participant that don't move. Professor Kapil Sharma is going to take the next lecture.
Okay. All right. All right. Okay.
Thank you, sir.
Yes, sir. Yes.
Namaskar, sir.
Good evening, sir.
Good evening, ma'am. Good evening.
Can I give some instructions to the participants in the meantime? Just for 3 minutes.
Sure, ma'am. Sure.
I just want to repeat that there are certain instructions for the participants. Attendance will be via Google form, and link will be shared just in the chat box, and you have to take the visual yourself that when it comes, you have to fill the attendance session wise. Okay, and then you can be asked to switch on your camera at any moment because we want to capture it. And then third, the most important is that you have to log in with your official name ID so that it's easy for us to allow you. Otherwise, you may not be allowed in. So these were the main important instructions for the participants, and do join in time. Like you have to join 5 minutes before the lecture starts. So now it's the time for you to start. Professor Kapil Sharma, welcome to you in the second day of this workshop. Now you can start.
Thank you, ma'am. Thank you.
Okay, sir.
So if you remember in the last lecture, so it's audible, ma'am? Am I audible?
Yes, sir.
Yes,
Oh,
sir.
Yes.
Thank you. So in the last lecture, we were looking for the solution of where is
Initial
my
value
pen?
problem.
Yeah. For the first order initial value problem, y prime is equal to fxy with the initial condition y at where x naught is any point in the domain of the differential equation, y at x naught is equal to y naught, and we assume that let y be a solution of this initial value problem. So then we were looking for yx. We kept yx on the left hand side, and we are looking the right hand side as a given quantity. If we would be able to find the right hand side in the given term, so then our work is over and we are able to solve that. But as I told you in the beginning that we don't have any procedure by which we can find the exact solution of this first order initial value problem in the journal form. Means take any value of f, of course certainly with satisfying the existence uniqueness property of the solution. So even then we don't have any procedure. So it means that it would not be easy to keep the known thing on the right hand side. So there will be certain issue would be there, and to settle these issue, so we will make some approximation. So that's why we will study these method under the umbrella of numerical analysis. Yes, somebody was saying something. Yeah, so my basic motive, so what are the given thing? Actually x is given here because x is a independent variable. X is given, f is given, and y naught is given. Means the value of y at x naught is given. So now what should I do? Means how we should move. So basically we should convert this y thing, y at x, rather y at x naught. So then things would be somehow known there initially. So I involve x naught, I add x naught and subtract, and in that case there is no harm in doing that. So I add x naught and subtract x naught. This thing is clear. I know x, but I don't know the value of y at x. So now my objective, I don't know y at x naught, but I know y at x. I don't know y at x, but I know y at x naught. So using the Taylor's method, Taylor series method, I will expand this around x naught. So this is y at, I use Taylor's series. I will expand this y at x naught plus x minus x naught. Suppose I am denoting this by h. So basically this is equal to y at x naught plus h.
X.
So now, of course, h depend on x because x naught is fixed. So what we have the first term is y at x naught plus
H.
Prime y prime. Hello.
Yes, sir.
Yes.
Yeah. Somebody was saying something.
No.
No, sir. Y dash X naught.
Y, yeah, okay, just y dash at X naught plus H square by
H square by 2
Factorial.
factorial or F double Y
Yeah.
double dash
Y double dash at
X naught.
X. Yeah, in that way. So we have now look, we can write the journal term dot the or we can write this in a remainder form.
H ki power n
and
upon n factorial
upon n factorial y n at x naught, and we will write the last error term as
h ki power n minus 1 n minus
n plus
1
and n plus 1 divided by
n plus 1 factorial
y at n plus 1 at derivative at xi, where xi belong to the interval around x naught. So in that way we have written this, otherwise it has the infinitely many terms. So whatever the rest term is there, so that contribution is taken care of this one. So this thing, so now we will look at what are the quantity which we are aware, in this thing. So if we look the first one, so y at x naught is given, am I right? It is known, so nothing to worry because it is given. This is y naught. Now we are coming to the second term. In second term we have 2 h and y prime at x naught. So tell me whether h is given to us or no. Anybody can answer?
Sir, arbitrary.
Yeah, h is known or not? Hello. Yes, somebody answered. Yeah, h is known because h is equal to x minus x naught. So x is also independent. So where we are looking for the value of unknown parameter, so that is or unknown that is given to us. So this is x is known, x naught is known, because these are the independent variable. So h is known. Now we are coming to y prime at x naught. So y prime at x naught is given.
Yes, sir.
Yeah, well, from the differential equation we can find. Am I right? So it means that if we look here, so this is y naught plus h, h is also given, and y prime at x naught is f naught. F naught means f at x naught comma y naught. So this is given. Now we are coming to the third one, whether this y double prime at x naught is known, because f is known to us. So these two terms are now known to us. So now we talk about the third one. Anybody can answer? H is known, so of course h squared by 2 is also known. So now we are just caring about this y double prime at x naught. So whether it's given, hello, yeah, y double prime we can write. Yeah, y double prime can be written as, first we will write y double prime x, and then we will replace x by
X dash naught.
Yeah, x naught. So dy by dx of dx of y prime, and y prime is nothing but f. Am I right? And f is a function of two variable x and y. So we can find its value because f is known. So we can find its value by the chain rule. So just quickly tell me the what will be the value of f, dy by dx of f. Please tell me. Quickly calculate. All of you should calculate and tell me. So we have h squared by 2 what happened? No. Where is my pen? Go. Yeah, so just quickly calculate this y double prime and tell me by curly f by curly x into dx by dx plus curly f by curly y into dy by d by dx dy by dx. Am I right? So I'm not able to write here. So where is this pen? How it will? Okay, yeah. So so this is 2, and tell me what value we are getting for y double prime. So f x means curly f by partial derivative of f with respect to x into dy by dx dx by dx1 plus curly f by curly y partial derivative of f with respect to y into dy by dx means y prime, which is again f. This thing is clear. So yes, we are getting this at x naught. Am I right? At x naught. This thing is clear. So f is known. If f is known, so its partial derivatives are we can calculate. So it means that the third term is also known. Now go for the fourth term. What will be the fourth term? Will be h cube by factorial 3, or we can write directly 6, whatever you are writing, and then quickly do one what will be the y triple prime? Y triple prime is equal to y triple prime is equal to dy by dx of y double prime, dy by dx of
fx plus fy of x.
yeah, fx plus. So just quickly calculate
F
that all
double
and
fx
simplify.
plus f of xy into
Yeah, f, just tell me f
xx plus
fxx. So did you calculate on your notebook? Quickly do that and tell me the simplified one. Plus so anybody calculated?
The 2 times of mixed derivative fxy plus fyy.
2 into
2 times mixed derivative fxy
fxy
plus fyy.
plus fyy means the
At x equal to x naught.
yeah, at x equal to x.
ये सब कुछ पढ़ा हुआ है. Your writing is not visible, sir.
Screen is not visible.
We can see
Visible.
your screen. It's visible, sir.
Yeah, so in that way we can find, if you look, I mean, if we go for the fourth derivative, means fifth term, so that can also be calculated. Am I right in that way? So now, I mean, you would say that, sir, okay, everything on the right hand side seems to be known. Am I right? Because every term we can calculate. Of course, we put the restriction on f, that it has it is sufficiently smooth, or it has the desired regularity, means its derivative exist. But I mean, on the right hand side, everything is known to us. Am I right? So you would say that, sir, but you claim that we don't have any procedure to find the exact solution of the problem. And in that way, we done that. But here the problem is that we don't have any procedure to sum up this infinite series. We can sum this infinite series in a particular cases, but in journal we don't have any procedure. So that's why we आसमान से गिरे खजूर पे लटक गए. Am I right? So what we need to do now? We need to now truncate. Am I right? This series, or we will count only the finitely many terms of the series that can be sum up. Am I right? So in that way we have, and whatever, I mean, if we keep one term of the series, so then we will have one method. If we keep two term of the series, so then we will have another method. If we keep 3 term of the series, then we have another method. So in that way, using this approach is known as the Taylor series approach. Is known as the Taylor series approach, and by this approach we can generate a family of methods. Am I right? So now we should look some property of this type of method. If you look here, so, and what will be the error in this case? Suppose I keep 3 terms of the series, so then order will then error will be this one. means h cube by 6, and it's I mean unknown fourth derivative at xi. So this will give us the error. Am I right? So what is the beauty of this approach? The beauty of this approach is that we can generate a method based on Taylor's series method, Taylor's approach with desired accuracy. Am I right? If suppose we generate a method keeping two terms, and then we compute the approximate solution, we feel that the approximate solution is does not have the desired accuracy, so we can take another one, we can take 3 terms. So then of course we will have the better. And so in that way, if after keeping 3 terms in the method and we are not getting the desired accuracy, so we can have the fourth term. So it means that we can have the desired, we can generate a method with desired accuracy based on Taylor's approach. Are you agree?
Yes, sir.
So I think this is the most desirable condition in the approximation theory. Am I right? If somebody say that, okay, I will give you the approximate solution, and with the rider that, or with your desired accuracy. So then what else you want? So it means we should think here. Then why the other method came into the picture, like Picard method? Did you heard Picard method for the initial value problem? And Picard method, modified Euler method, Euler method, modified Euler method, trapezoidal method, Rangakuta method. So then what is the fun for searching these type of methods? So we have to have some drawback of Taylor's method, which encouraged us that time to generate some other class of method. Am I right? So anybody can answer? Anybody can tell some drawback of Taylor's based method?
Here we need to find the many functions derivative of functions.
We need to find. Please speak loudly.
Yes, we need to find many function evaluations with derivative. Many derivatives.
Yeah. We need to compute the derivative. Am I right? We need to compute the derivatives. Am I right? So we need to compute the derivative, and particularly it's fine for the scalar when we are considering this scalar initial value problem. But when we have a system of first order initial value problem, so in that case these derivatives will convert to a Jacobian, and it's a full matrix. Am I right? So it's a very cumbersome. Even in this case also, if you go for the y4 or y5th derivative, so then it seems to be cumbersome. But okay, chalo, nowadays we have the machine to do that. But when we go for the system of equations, so in that case, when we compute the Jacobian, means the derivative, so there Jacobians comes into the picture, and to compute that, it's very computationally costly. And if we have a very big system of equation, so then in that case, sometime our supercomputer will not work. So that's why we are not interested to compute the derivative. So then we come to the second approach. I don't think that I need to give you some example for solving that. Even I can give you in the assignment. So you can do practice. So I'm just giving here the flavor that how the research might have evolved when it was done that during that period. Or you should think that how we should approach to solve our problem. So first we should narrow down our problem, or we should concentrate that what are the drawback, and then how we should tackle this. For example, as we start from here, am I right? So in that way we should work. So now our problem is that we wish to get rid of these derivatives. So the basic tool to get rid of derivative is so the to get rid of the derivative is the integration. Am I right? So now we will integrate this initial value or differential equation y prime is equal to fxy from x naught to x naught to x. So please integrate that on your notebook. So what we are getting yx yx is equal to yx is equal to, please do that quickly. I'm just writing the y at x naught y at x naught plus x naught to x. Am I right? F x comma y dx. This thing is clear. So to get rid of the derivative, the best way, just integrate that, and we have done that. So now look on the right hand yx, of course it's a solution of the initial value problem, so we are looking for that. Now we are looking the second term is known to us. Now tell me whether we can find this integral or not. Please answer. Hello.
Yes,
yeah,
sir.
of course in journal we cannot find this integral. Am I right? So then we should look that where is the problem. We are generating here the Picard method. Picard's method. So now tell me that what is creating a problem here. Here this y unknown is sitting in the right hand side under the integral sign. So this is basically creating a problem. Am I right?
Yes, sir.
Yeah. So then what we will do, we will basically generate a sequence approximation, and of course you might have studied in the existence and the uniqueness of the solution of this initial value problem, that sequence converges to the exact solution. Am I right? Why? We keep so how we generate a sequence? Anybody can answer? In that way we will do that. Basically for generating a sequence, what we require? Yeah, just just give answer, whatever you feel. It's not necessary that you will have or any everybody.
Sir, we need y1, y2, y3 and so on.
Yeah. So, but we cannot write infinitely many terms. So that's why what we require one recurrence relation.
Recurrence relation.
Yeah, one recurrence relation and first term of the sequence. So how we will generate a recurrence relation here? So we keep unknown on the nth place. Am I right? This is
Yes,
y
sir.
naught plus and this whatever sitting is
Y n minus 1.
yeah at n minus
1.
1 x naught to
X.
x f x
Comma y n minus 1.
y n
One.
minus n minus 1 dx. And also, as I told you, that we also require the first term of the sequence. Now our sequence is this one, y n. Am I right? So I require y0 also. So what is y0? Y0 I am taking y at x naught, y at x naught, which is given to us. So now we have this sequence. Am I right?
Yes, yes.
Yes, sir.
So now this sequence is known, and we know that, or we can easily prove that this as n tends to infinity, this sequence converges to yx, which is a solution of the initial value problem. Am I right?
Yes, sir.
Yes.
Yeah. So it means that as n tends to as n is bigger and bigger, so the term of the sequence will be closer to the exact one. Am I right? So in that way, we will generate a sequence of approximation, and each member of the sequence is an approximation to yx. This thing is clear. So if we take first term of the sequence, so then we will get an approximate value to the unknown. If we will have y2, so that will give a better than y1, y3 better than y2, and in that way this thing is clear. So in the beauty of Taylor's approximation we retain, and of course here we need not to compute the derivatives. Am I right? So we will get rid of the computing the derivatives, and we retain the beauty of the Taylor's approach, that this approach also give us answer with the or approximation with the desired accuracy. Am I right? So you should say now that now I think we should stop searching other method, but still we are aware that there are certain other method also. Euler method, modified Euler method, trapezoidal method, Rangakuta method, multi-step method. So anybody can now draw back of these two or this class of method? Anybody can answer? So basically, what we are doing, we are approximating the function fx comma yx by another function in the interval x naught to x. Am I right? Or if we just come back to the Taylor's method. So what was the Taylor's method basically? In the Taylor's method, the yx is given or error in the Taylor's method, if I call it rather. The error in the, even here also we can explain, but by the Taylor series we can easily, error is after keeping the n term. So error is h power n plus 1 means h is x minus x naught power n plus 1 divide into y n plus 1 derivative h hi divide by n plus divide by n plus 1 factorial, n plus 1 factorial. This thing is clear. And let us assume, as I told you, that we have this y is sufficiently smooth. So let's assume that y belongs to C n plus 1 C n plus 1 on I, means it's nth derivative, n plus 1th derivative exists and continuous, means it is bounded. So suppose let us assume that y n plus 1 x xi is bounded by m. So then this will replace by the bound, means capital M, where capital M is the bound of the derivative n plus 1th, and this inequality will become inequality. So error will be less than equal to x minus x naught n plus power n plus 1 m n plus 1 factorial. This thing is clear. So now look on which now error depend. Error depend on this term. Are you agree?
Yes,
if x is far from x naught, so then error will be more. Am I right? If x is far from x naught, so then error will, or as x increases, or as x minus x increasing, the error is keeping increasing. What does it mean? It means that if we simulate any our problem for longer time, our result going to be worse and worse. So it means we can say that. So same thing will apply in the Picard also, because in Picard also basically we are taking approximation. We are approximating this function fxy by fxyn. Am I right? In the interval x0 to x. So if this interval is going to be bigger and bigger, so then this approximation will be worse and worse. You might be aware about in the Riemann integral. In Riemann integral, basically what we do, rather taking approximation in a bigger interval, we divide that into a small subinterval and then take the approximation. Am I right? So if we take approximation in a bigger interval, so then it would be worse. This thing is clear. So that's why these both the method, this class of method, which is known as the closed approximate methods, are biased towards the initial value or initial node. These methods are biased towards the initial node. So it means that these methods are biased, but we are interested to develop the method which gives us uniform result or uniform error on the entire domain. Am I right? So that this drawback of this class of method give us to research the other methods which are known as the discretization method or step marching method. Step marching method. Step marching. Step marching. Step marching method or discretization method. Discretization method. This thing is clear. So anybody have any doubt till here?
No, sir.
Yeah. So what we do, first, as I have given you the hint that what is creating a problem now here, because we are taking approximation on a bigger interval. So now what we will do that we will divide our domain. We will divide our domain into a small pieces or small subintervals, and then take approximation on the smaller part. Am I right? So in that way we will get rid of this problem. So first we should identify what is the problem, and then we should answer that. So our problem is that because we are taking approximation on the entire domain, x0 to x. So now what we will do, first we will discretize the domain. Suppose this is our domain. This is x node, and this is say capital X. This is capital X. So what we will do, we will discretize the domain, or we will go, basically we have to solve problem on the entire domain, means x0 to capital X. Am I right? But how we will move that? We will discretize the domain into a small interval, and then taking approximation from here to here, we will reach here. Then using this value, we will reach here. Using this value, we will reach here. Here it is giving y naught. Using this value, we will predict this one, y1. Using this y1 now, we will predict y2, and so on. This thing is clear. Suppose this is xn. So xn is equal to capital X. So in that way, we will get rid of that, and this class of method is known as the step marching. Why step marching? Because we are moving step by step rather than jumping from here to here. We are going in small steps. Am I right? And then we are reaching to the final one. Or discretization method, because basically what we are doing, we are doing that the discretization of the domain, entire domain. We divided the entire domain into a small pieces. This thing is clear?
Yes, sir.
Yeah. Now this step marching method are classified into two classes: single step and multi-step. Multi-step. Okay, I'm running a new one. So suppose we have this is our domain basically. Am I right? So what we are doing? We are doing, suppose this is X node, and this is our capital X, and at X node I know the value, and now we are moving step by step using the Y1 and Y node. We are predicting the value at X1, say it is Y1, then using Y1 we are predicting this at Y2, and of course these step also may vary. It may be uniform step size or it may be vary. So certain thing would be X3, Y3. Using Y2 we are predicting Y3. So in that ways, now suppose I have to predict X4. I have to predict X4, the value at X4. So now we have Y3 with us. I know the value at X3, we know the value at X2, we know the value at X1. When I am predicting the value at X1, so then I have only the one value at Y1. But when I'm predicting the value at X node, so now we have Y0, Y1. Now, when I'm predicting Y at value at X3, so then I have Y0, Y1, Y2. Am I right? Absolutely. Hello? Yeah. So in that way, in that way, when I'm predicting at X4, so of course I can use only the previous value, then we can get that also. So if we are using only the one value, so then it's fine. So we have the single step. To predicting the next, we are using only one step. But as you know that if you have more information, you use more information for the predictions. So of course you would have the better result. Am I right? Also in that way, suppose you are using now Y2 also, Y2, Y3 for predicting at X4. So now you are using 2 step. So it means that then your method will be 2 step. Am I right? 2 step. If you are using 3 step to predict Y4, so then your method will be 3 step. If you are using K step for predicting the next value, so then method will be K step, and these are known as the common data multi step method. So tomorrow first we will study the single step method, and then we will move to multi-step method. So today homework or assignment is that at least you people should do two example for Taylor's and Picard method. You should just, so then you will be able to see, you can take any book. You can take M.K. Jain, or you can take Burden and Fear from any book, or Lambert. I'm afraid that you would have this some numerical examples, some theoretical things would be there. So at least then you would be able to visualize that what we have done. So I think I should stop here. So any doubt? Anybody have any query? So I can answer. We have a few minutes. Yeah, ma'am.
Yes, participants, you can ask your questions from anyone.
No question, sir.
No question.
No question,
Okay, sir. Thank you so much.
Okay, thank you, ma'am. Thank you.
Thank you, sir.
Thank you.
Of course, sir. See you tomorrow at the same time.
Okay, thank you, ma'am. Thank you very much.